I'm going to try to explain 10 Scala features that are vital to understanding pretty much any Scala projects. Some of them are trivial, some of them not so much. Let's get to it. Hey, Vlad here from devinsider.com. Welcome to another video. Over the years, I've made hundreds of Scala-related videos, and I even taught Scala as a first programming language to people without any prior programming experience. That said, I frequently get questions about some of Scala's features because the answers to them are buried somewhere in gigantic playlists. Hopefully, this video will become somewhat of a go-to place to find them. Also, I have a 3.5-hour Scala Crash Course, if you're interested. In any case, let's go through them one by one right after the message from our sponsors, scalajobs.com and rustjobs.dev. Check out the links in the description below if you're looking for a job. This video is also brought to you by awesome people like yourself who support me on platforms like Patreon, GitHub sponsors, and brand new by joining the YouTube membership program. Your contributions go right back into this channel. They allow me to pay for a video editor who frees some of my time, which I then again choose to spend with you, whether it's during live streams or answering your questions on Discord. Also, you get to see my videos before everyone else, which is nice. There's many of you and only one of me, so all it takes is $1. Thank you. All right, let's start our list with the right associative operators. Whereas most languages make a distinction between operators and functions and/or methods, Scala does not. Every operator is merely a method call, and Scala syntactically allows you to make the call look like an infix operator. Semantic highlighting that was recently introduced in Metals helps a ton. In Scala 3, there is an additional constraint on non-symbolic method names. You can only call them via the infix operator notation if they're explicitly marked with the infix keyword. Now, usually the method in question is being called on whatever is on the left from the operator, and whatever is on the right becomes the argument to that method. However, if the method name ends in a colon, when called via the infix operator notation, the sides are swapped. The object is on the right, and whatever is on the left becomes the argument. While in theory it sounds like an annoyance that you need to pay attention to at all times, in practice there are very few right associative methods, and most, if not all of them, are just concatenation methods on the collections in the standard library. The next feature on the list is string interpolation, which is a way to create strings while splicing arbitrary expressions into them. On the surface, string interpolation looks pretty straightforward. Just prepend the as character to your strings, and now you can write full-blown expressions surrounded by curly brace, prepended with a dollar symbol. You can even leave out the curly braces for simple expressions like variable references. There are several interpolators out there with slight differences, and you can even define your own. The built-in ones are the S interpolator that we just discussed, the F interpolator, which allows you to insert printf-style formatting options into your strings, and the raw interpolator that allows you to leave unescaped special characters in there like \n. It's still an interpolator though, so you can splice full-blown expressions into it. That's all for the built-in ones, but there are many interpolators out there created as parts of libraries. For instance, there is Skunk, a native Postgres driver which comes with the SQL interpolator. Also, there are libraries like SCTP, which comes with the URI interpolator. You get the idea. The next feature on the list are Lambdas, also known as anonymous functions. Can you imagine being so famous that you're known even though you're anonymous? Anyways, lambdas are literals for functions. The same as you can create things like ints or booleans out of thin air by using their respective literals, you can create functions out of thin air as well. They just sugar two instances of anonymous classes behind the scenes and are used literally everywhere throughout the language. Pun intended. I can't go into details in such a short video, but the TLDR is that you have a parameter list that is separated from the body by an arrow to the right, which is an equal sign followed by the greater than character. I love ligatures. When all the types are fully known, meaning when your code expects a function, and you use all of your parameters only once in exactly the same order as they're defined, there's even more syntactic sugar on top. Instead of first declaring the parameters followed by an arrow to the right and then using them in the body, you can only write the body and replace the parameters with underscores. The underscores don't work with string interpolation and honestly a bunch of other things like if expressions, for example. Essentially, this special syntax only works for very simple expressions. And when you have a method that fully matches the signature of an expected function, the compiler will convert it for you, so you don't need to wrap it in an extra lambda. This is called ADA expansion, same as beta, just without the B, which brings us to partially applied functions. Not partial functions. We'll get to those in a second. We're talking about partially applied functions, which is a way to adapt the signature of a method before ADA expansion kicks in. Personally rarely use partially applied functions. I prefer to either manually wrap my methods into lambdas or rewrite the initial methods into their curried versions, which brings us to the next point: function currying and higher-order functions. A higher-order function is a function or a method that receives one or more other functions, usually lambdas as parameters, or produces lambdas as a result. That later part is often forgotten because most of the times higher order functions receive other functions as a parameter. Higher order functions is a classic concept from functional programming, and it is syntactically supported by most modern programming languages, even though some of them took almost a decade to implement it. The most canonical examples of higher-order functions are methods on the Scala standard collections library. The method map knows how to traverse the given collection and produce another one as a result. You merely pass in a lambda so that it knows how to transform each element while it does so. The same goes for the method called filter. It knows how to traverse the collection in question and produce another one as a result. You merely pass in a lambda, which acts as a predicate to decide whether to keep the element or not. Yet another example is a method called sort. It knows how to traverse a collection and produce a resulting one. You merely pass in a lambda, which acts as a comparator that decides the order of the resulting collection. You get the idea. Higher order functions are everywhere. Now, curried functions are a special case of higher order functions. Those are the ones with at least two parameter lists. They're called after Haskell Curry, an American mathematician who is very well known for the Curry-Harvard-Lambda correspondence. I have a video about it, you might want to check it out. He neither invented the concept of currying nor Haskell the programming language, but both of them are called after him. Now, in programming, it's trivial to have functions or methods with multiple parameters. We have methods like this all the time. However, in math, analyzing such functions is anything but trivial, so mathematicians use a trick. Instead of having a function which takes, say, 3 parameters, they use a function which takes only 1 parameter and returns a function which takes the remaining 2. To be more precise, the second function doesn't take the 2 parameters either. Instead, it takes the second parameter and returns a third function which would take the third parameter, and that one returns the final result. If you call these functions one by one without storing the intermediate resulting functions, it kind of looks like you're calling a function which has 3 parameter lists. In fact, Scala allows you to use multiple parameter lists when you're declaring functions as well. Behind the scenes is function currying, of course. We're still not done talking about functions. It's almost as if Scala was a functional programming language or something. We've talked about partially applied functions before. Now the time has come to talk about partial functions. Whereas regular functions are defined for the entire domain, meaning for all possible values for the types of the parameters, a partial function is defined only on a portion of those values. For instance, instead of a function that takes a boolean, you'd have a function that only knows how to handle the true case. If you pass in false, an exception will be thrown at runtime, which is why you should be extremely careful with partial functions. We like type-safe things in Scala, and partial functions go a little bit against this philosophy. Partial functions are merely a syntactic construct. Their only purpose is convenience. In fact, they're so convenient that we even sacrifice common sense for it. For instance, if I were to write a higher order function that wants a partial function as its parameter, I should be allowed to pass in a total function as its argument. While in reality, this relationship is reverse. When a total function is required, you can pass partial functions as argument because partial functions extend the functionality of total functions. This is obviously an issue because the receiving function has no idea that what was passed in deals only with a portion of the domain. Again, all of this was done on purpose for the sake of convenience, which brings us to the next point, which is pattern matching. Technically, it's still part of the same point. Pattern matching is a feature that Scala newcomers fall in love with. It's an extremely powerful syntactic sugar on top of branching. And since we've been doing if-else thingies since the dawn of programming, your entire codebase might accidentally end up looking like a gigantic pattern match. I recently made a video exactly about this point. You might want to check it out. We have a plethora of built-in patterns. We have a pattern that matches on constants. We have a pattern that matches on variables, types, constructors, a bunch of other things, and even extractors that you can define yourself. Did I mention that Scala stands for scalable language? Anyways, the true power of pattern matching comes from 3 things: nested patterns. Try doing that with nested if-else expressions, I dare you. Pattern matching appears in tons of places throughout the language, and from the fact that Scala is a very deep language, meaning that it has only a couple of features, but they can be combined in seemingly infinite ways. Some of them would take me minutes to explain a single line of code. Like this one, for example. Do you recognize the things that we discussed a couple of minutes ago? Please watch the video that I just mentioned to realize that pattern matching, even though it's powerful, is just a stepping stone to something bigger. Don't make the same mistake as literally every other Scala beginner. Don't overuse pattern matching. It's not even just a Scala program. The Rust community is going through something similar as we speak. Oh, look, pattern matching. It's so cool. I don't mean to sound arrogant, but it's sometimes adorable to watch other programming languages that are somewhat late to the party. Literally every JavaScript developer out there who started using TypeScript went, oh, look at that. Types are useful. Well, good morning. Let's talk about high-kinded types now. We humans frequently like to group things, and so we use synonyms to the word group, things like types, kind, pattern, class, and so on. High-kinded types are named analogously to higher-order functions. These are types that are somewhat incomplete, so you need to pass in another type to construct the full type. So similarly, how a higher-order function would receive another function as a parameter, a higher-order type would receive another type as a parameter, which is also why they're sometimes called type constructors. As an example of the problem that high kinds can solve is the ability to define traits or functions which work with any kind of list, whether it's a list of ints, strings, or even dogs. Not only that, but I also allow you to write traits or functions that work with any kind of parameterized type, not just list, for instance, option or IO, just to name a few. As long as those types are of the same kind, namely a type constructor with a single argument, they'll fit. This video is getting kind of long, so let's move on to implicits and type classes. Implicits are arguably the most powerful Scala feature, and with great power, oh Jesus, I can't do it. If you're not familiar, implicits give the compiler a second chance on failed compilation. Whenever your code doesn't compile for type mismatch reasons, the compiler won't give up. It will look in a few special places for functions that will allow you to convert one type into another to make your code compile. There are only two situations when the compiler will even attempt to do so. Number one, something wants an apple and we give it an orange, and number two, you're trying to call a method on an apple that doesn't exist. The first case is sometimes called implicit implicits or implicit conversions, and is generally speaking frowned upon, because unless you have some fancy IDE, it's not always obvious that an implicit conversion took place. There are many cases that are obvious, like for example a widening of a type like int to a long. However, you could also define your own implicit conversion that would go the other way and cause all sorts of havoc. The second case is sometimes called explicit implicits or extension methods, and this one is pretty much loved by everyone. Scala 3 has a new syntax for extension methods, which makes them even more pleasant to use than before. By the way, guys, if you want details, I have videos about all of these things, so you might want to check them out. Now, the most interesting use case for implicit is actually another one. It's the implementation of the adapter pattern. It's just that you don't have to pass those adapters explicitly. The compiler will do this for you, assuming that your types are unambiguous, of course, and also that there is only one implicitly available adapter that matches those types. In Scala 3, the dedicated keywords for type classes are given and using. Let's move on to number 9. We're almost done here, I promise. For comprehensions. Now, for comprehensions look like for loops, but if you do look at them like for loops, do yourself a favor and forget everything you know about for loops, because for comprehensions are not for loops. Their full name is monadic for comprehensions. Without going into details, a monad is just an interface with a method called flatmap on it, and if you want details, I have multiple videos about monads on this channel. Now, nested flatmap calls is a one-way ticket to callback hell, and so a for comprehension is merely a syntactic sugar. It's a bunch of nested flatmap calls followed by either a map if the yield keyword is used, or a call to for each if the yield keyword is left out in Scala 2, or the do keyword is used in Scala 3. In Scala 3, you can even leave out the curly braces. I have a full-blown video about for comprehensions alone, obviously, so you might want to check it out. Number 10, algebraic data types, or ADTs, which are a collection of types that can act as one. For instance, a color can be either red, green, or blue, or an option can either hold a value, so it can be a sum of some value, or a none if no value is present. Another way to look at them is as types that have multiple ways for constructing them. They're also known as sum types, a rather mathematical way of looking at things. Remember Haskell Curry? Blame him. It's hard to explain, so check out my video about the Curry-Howard-Lambda correspondence if you're curious. Another name they go by is coproducts, a concept from category theory, another thing that we won't get into today. In any case, they were a bit cumbersome to define in Scala 2 and look pretty elegant in Scala 3 with the enum keyword. There are some limitations to the syntax though, in particular the nested enums are not well supported yet. Alright, I have a bonus feature for you, but before we get into that, I also have an honorable mention. Case classes. which is a way to define data structures. They are loved by everyone, and the only reason that they're not part of this list is because I wanted to limit it to 10 items, and also they're pretty straightforward. A tiny public service announcement: please stop slapping the case keyword on your classes just because you don't want to use the new keyword. In fact, in Scala 3, you don't need to use a new keyword in most cases because of guys like you. All right, let's get into the bonus feature and wrap this up. I couldn't leave it out because it's my favorite one. In fact, it's two features: top-level definitions and exports. Top-level definitions are pretty straightforward. In Scala 2, you weren't allowed to define vowels, vars, defs, lazy vowels, and types at a top level. In Scala 3, you can. I love this feature because when packages are shared across multi-project builds, package objects are not enough because you can have only one of them. Exports, which can also appear at the top level, are an awesome feature which allows you to favor composition over inheritance. I made a video about it naturally. When exports appear at the top level, they save you from repeated import statements, which is a typical cause for a lot of merge conflicts. Imagine exporting something like zio.star in one place instead of having an import in literally every file. That would be awesome. Unfortunately, this feature is currently limited. You can't export entire packages. It's only a technical limitation though, and there is currently an ongoing discussion on the Scala contributors forum to improve the state of the art. You might want to contribute. For now, the best you can do is use the -y imports compiler flag. It's almost available in Scala 3.3. It's already merged and is available since RC1. 3.3 is almost out, by the way, which removes the limitation for the indentation-based syntax, a highly controversial feature that I also made a video about, of course. Anyways, as already mentioned, arguably the most powerful Scala feature is not any of those that I mentioned on this list. Instead, it's the ability to combine them in seemingly infinite ways. It's a two-edged sword though, so don't cut yourself. I hope you enjoyed this one. Check out the previous one and I see you in the next one. For now, as always, it's been Vlad from devinside.com. Don't forget to like this video if you did, subscribe if you want to improve the developer inside you, and if you wish to contribute to tech education, just click the join button or check out my Patreon or GitHub sponsors and watch my videos before everyone else. And most importantly, take care.